each operation and think about it in terms of what's going to actually happen when the processor executes the code. And that's the formula for describing every computation that happens in a software system. So these are the building blocks of the source code. This is the bit-accurate representation that, as we call our complete representation of your software system, the software DNA map. We can translate that into this bit-accurate representation for the purpose of doing SAT-based analysis. So Coverity is the first provider of SAT for static analysis, and this is how we drive that false positive rate right into the ground, and yet still maintain scalability to millions and millions of lines of code. It's by taking a high-level control flow graph representation, turning it into the ands, ors, and nots, and that is what really allows us to take this next step from second to third generation static analysis. A couple of the advantages of this particular technique, it allows us not to just cover all the paths through the code, and this is what traditional data flow analysis gives us. You're pushing through all the different paths of the code, true and false, for every different branch. But with SAT now, because of this bit-accurate representation, we can cover all the different possible values for each variable on the paths that we determine are interesting from an analysis perspective. And so we're extracting the values from any given solution that the SAT solver gives us. The complementary nature of SAT-based techniques as well as traditional data flow techniques allows us to find classes of defects that were previously undetectable or undetectable without a huge amount of false positives. And that's the real benefit of marrying these two technologies together. So how in particular do we leverage SAT to prune out false paths, to make sure that when we're reporting a defect, it's a real defect? So let's bring up the poll results from the last poll to see, what your view on false positive rate should be. So, not surprisingly, everybody wants to have a low false positive rate. The majority or plurality of people responded with 15%. A few people said 20 was okay. Very few people said 25 or 30. And as I mentioned, even in the second generation, those false positive rates could be double that or more. And so, our experience with our commercial customers is that, everyone's right on the money with 15%, 15%, 20%. That is right where you need to be to make it usable. And so, here's how we use SAT to deal with this false positive problem. Data flow analysis has a limitation in that the highest cause of false positives is on false paths. And a false path is something that occurs when a data flow finds a defect, but it's on a path that cannot actually execute when you run the program. There is some logical inconsistency between the conditions that need to be true and false in order for that path to occur, so it's impossible to execute. And obviously, if the analysis reports to you a bug on a path that's impossible to execute, it's a false positive, it's noise, it's wasting the developer's time. And it's keeping you from actually being able to deploy these tools in a fashion that would allow you to run them every single day in an Agile development or in a traditional development environment. And the goal, as Tom mentioned, is we want to be able to run these things every single day. And so what SAT allows us to do is it allows us to pick out those paths that would be infeasible and just throw them away. And so the process is you let data flow analysis do its thing. It's going to run over the code base. It's going to identify the paths that it thinks have problems. But then you combine that with SAT, and for each path that you're about to report a bug, you take a look at all the conditions. You pull all those conditions out, and you convert them into their bit-accurate representation, plug that into a SAT solver, and ask the SAT solver, is this path actually feasible? And if SAT comes back and says, yes, it's feasible, here's an assignment of values to variables for which you can actually take this path, well, you know that there is going to be some runtime circumstance in which this path occurs. And you should report the bug because it's something that's actually going to hit. Whereas if it comes back and says it's unsatisfiable, that means there's some contradiction in the path. That means this path is infeasible, it's a false path, and you shouldn't report a bug in that particular case. And so that is what really allows us to push this false positive rate lower by combining the strengths of data flow analysis and uncovering bugs down path with the ability to prune out the ones that are incorrect using SAT. We've had a lot of early successes. We've been rolling this into the market over the last month or two, and obviously over the last 5 years, we've collected lots of stories and code snippets from people about false positives because of data flow analysis. And we've eliminated dozens and dozens of categories from our internal defect tracking system of things that our customers have reported to us over the years, and SAT just cleans all of those things up. And the real benefit, of course, is that developers spend more time on real issues, more time than implementing features in their product, and we've vetted this technology over millions of lines of open source software to experience this reduction in false positives. So here, just to give you a sense of what it looks like from a numerical standpoint, as I mentioned, second generation gave you maybe 50% false positives. Now Coverity, with this SAT-based technology, can bump up the real defects into the 80 to 90% real range. And just to give you a glimpse into what's coming next year and other ways we can leverage the SAT, as I mentioned, anything that's value specific, 100% value coverage, we're going to be able to tackle with an additional level of precision. Data flow analysis can find some buffer overflows, can find some string overflows, and we do that today. But now it's going to be even stronger with the addition of SAT, and we'll be able to dig into those types of defects and maintain that low false positive rate. And then another new category of checks that has previously been very difficult to uncover with just data flow analysis is in the area of integer overflows. Being able to examine all the critical computations in your code and being able to tell you if a particular computation has the potential for integer overflows. And not just that, but the values that would lead to that particular overflow. And then one other area where we'll be able to start doing some checking is to look at asserts. Developers use asserts a lot in their code now for verifying runtime conditions. You put an assert in the code with the hope that when you run the system, if that assertion fails, well, it's an earlier place in the code to find the defect. Well, leveraging SAT, we're going to be able to pull out all those asserts in the same format that you have in your code already and do some checking on them statically. So the more logic you put into your assert statements, the bank account balance has to be 100 at this point in the code, and so on and so forth, the more we're going to be able to check those logic properties for you at compile time statically before you ever run your software system. So it's a real powerful addition to what previously people thought, oh, you can't do that type of thing statically, you can't check any logic properties. But if you start putting these asserts in your code and leveraging them, we are going to be able to check those types of properties for you statically. So just to summarize, the third generation of static analysis, it has to be comprehensive and accurate. You've got to find really deep problems, and it's got to do it at a very, very low false positive rate. And really understand that the developer's time is valuable, and developers gravitate towards tools that will help them save time, not waste time, and which has been a problem for static analysis in the past. Just a couple of other bullets about some of the other technologies that we have. We have drop-in integration so that we can see every operation of your build system automatically. Without requiring you to change your build or change your code, we can start applying static analysis to your code base in a matter of minutes. And then, of course, we have a very effective workflow for mirroring your existing development process, whether it be Agile or traditional, to mirror what you're doing with our technologies and our products so that the defects that we find with static analysis, it can be run every day. Developers can fix them in short order and weed out a lot of those problems before they get into the QA phase of development. So with that, we'll take a few questions. Thank you for your time. So you can put the chat in, put the questions in the chat, and for either myself or for Tom, and we'll be happy to answer some of those. Okay, so the first question is for Tom, and it says, Tom was speaking about lean inspection methods. In how far is the SmartBear software approach of interest compared to the full-fledged methods as Fagan and Gilb inspection? Tom, you there?
So I think that utilizing something like SmartBear, there are a couple other tools that I've started to see out on the market, but